Hello, everybody. Welcome to my courtyard as we discuss today's subheading. As I start my screenplay, I welcome you to my courtyard, my family's backyard. I'm using it to display my my presentation today in my virtual class. As you know, this is my usual work. I design and I make contents in physics. I welcome you as we present today's presentation. And in today's presentation, I remain your teacher, your physics and mathematics teacher, Francis Lubakene. As I welcome you, and today I selected to discuss something in mechanics of motion. The mechanics of motion is, I picked a topic in senior 3 class, senior 3 physics. And I really wish you stand by me until the end of today's discussion so that you can really appreciate the fact that this is a simple topic. Today's evening, wherever you are, you enjoy together with me as you may watch only in the evening hours and you enjoy the topic. And today my coverage in the sub topic I selected. Today I selected subtopic of today I selected the subtopic. Today I selected the subtopic of acceleration due to gravity, and today's coverage will be basically not more. And by the end of this lecture, I expect my learners to define acceleration. I expect my learners to also know more about gravity, some bit of gravity. And I also expect my learners to be able to now explain acceleration due to gravity. And later on, you should be able to give practical examples of acceleration due to gravity in real life. I welcome you as we continue to display more. As we explained what acceleration is, what is acceleration? You need to know that let us take a practical example of a car. Imagine a car moving. We've all seen a car moving. Supposing it is a straight line. We need to start timing from a particular time of study for a particular point to the end point. Yes, as we display this car moving. Let the car move. Sorry, it has been so fast. It has been so fast. Let the car move slowly. Let the car move slowly. Can we display? We want to know exactly what acceleration is. Imagine this car, yes? And the car starts moving from a point A. We start our study from a certain point A as we end to a point B. As the car moves, starting from point A to point B. Yes. And the time stops at point B exactly. What do you think would have happened? Imagine there is a change in acceleration. Yes, I mean there is change in the velocity. The initial velocity and the final velocity varies. Yes, the initial velocity of the car at that point A and the final velocity of the car at the point B varies. Yes, so the variation of the initial from point A, as we start from point A to point B, yes, our study stops at point B. Yes, as the car reaches point B, the car reaches point B. So that means the initial velocity from point A to the final velocity at point B is quite different. Now, the difference in the velocity, as we rate it with respect to time, as we time it, yes, the initial velocity, let us say the initial velocity is at the velocity at A, while the car reaches point A. And the final velocity is as the car goes to point B. Now, the difference in the velocity of the car, and we rate it with respect to time. Yes, we take it to time, the time taken for the car to travel from point A to point B. is different. Yes, the time taken as the car reaches point B from point A to point B, the velocity of the car from point A to the velocity of the car from point B. Yes, the final velocity minus the initial velocity gives us the velocity, the velocity difference. And this velocity difference, we take it to the time. How long has it taken from point A to point B? Yes, how long it has taken will give us the time for the difference. Yes, the velocity from point A to velocity from point B. Yes, as the car reaches point B, the difference in the velocity will give us what? Will give us the time, the acceleration. So here we define acceleration as being the rate of change, the rate at which the velocity is changing from the initial velocity to the final velocity. That is to say, from velocity at point A to the velocity at point B. So the change in velocity, when you take it with respect to time, that is what acceleration is, as the car increases or decreases in velocity. Yes, and we should not forget that velocity is the distance covered per unit time, and it is the displacement, because it is a vector point, it is a vector distance. So it is displacement per unit time taken. So if it is displacement per unit time taken, we know that velocity is measured in meters per second. So in a mathematical expression, we know that acceleration is change in velocity over time. So the change in velocity is the velocity at B minus velocity at A. So velocity at A gives us the change in velocity. And now that change we divide by time mathematically, and we find that the change divided by time is acceleration. That is to say, change of velocity, change in velocity, we divide by time. Change in velocity divided by time gives us the acceleration itself. That is the rate of change of velocity. Yes, in other books they say, and it is not only other books, yes, it is also appropriate to say that the velocity is the final velocity. The acceleration is the final velocity minus initial velocity. As I may share with you a whiteboard, and mathematically we always go as mathematically. Let me load a whiteboard. As I load the whiteboard, I'm sorry, these gadgets. As I load the whiteboard, mathematical expression here states that the final velocity, let the final velocity be v. And then we subtract the initial velocity. Yes, and then we divide this change with the time. Yes, we divide with time, and we find that this change, we said this change divided by time gives us what we call the acceleration. So it is the final velocity minus the initial velocity divided by time. When we divide this change, because this is what we now see as delta. Yes, delta V, sorry, it is delta V. It is a delta V, yes. Delta V, we divide by time. Delta V all over time gives us what? The acceleration. You understand? So acceleration is delta V divided by what? Delta T. The change in velocity divided by the time taken to attain such a change in velocity. Right, as we may continue in our book. Our note today is telling us the change in velocity divided by time is acceleration. acceleration. Now, if we have known acceleration, and our discussion today is acceleration due to gravity. What about gravity? Yes, what about gravity? What do you understand about gravity? Gravitation itself is described as the force that pulls two masses together. Two masses are pulled together. That force exists between them. And all masses in the universe do exert attraction force between them as they coexist together. Yes, the coexistence of two masses together tends to give a force of attraction. And this force of attraction is dictated by the mass. Yes, the product of the mass divided by the square of that distance apart gives us the attraction force of gravity. Yes, as explained by one of our scientists, Sir Isaac Newton, in the 17th century. He formulated a law of gravity that holds for every particle in the universe, that the gravitational force between two bodies is directly proportional to the, as I may explain on my chalkboard here. Let me share with you a chalkboard. Yeah, we said the gravitational force, let me use a different color, a red one. Yeah, good. All right, the gravitational force F, yeah, they're saying the gravitational force F, yes, it is Fg, which is the gravitational force, is directly proportional to what? Is directly proportional to the product of the masses. Supposing we have two bodies, yes, let me first rub off this. Let me first rub off all this. Yes. It is directly proportional because supposing we have these bodies here. If the body of mass M1, this one is of mass M1, yes, and then another body of mass, sorry, this one is okay. Since there is a difference, there is dependence of the size, then supposing this one is of a smaller mass, if this one is of a smaller mass, if this body is of smaller mass M2, or depends on the size of the body, yes, smaller mass M2, not necessarily that the size depends and determines the mass, but let's say practically that this is smaller than the other one, and then it is of mass M2. If it is like that, and now the distance between them here, that distance here, let us call it R. Yes, this man said that the gravitational force that exists between these two bodies, the force of attraction between these two bodies, is directly proportional to the product of their masses. Yes, the product of their masses. Yes. Isaac Newton stated that the product of these masses, mass 1 times mass 2, mass 1 times mass 2, and then we divide by the square of the distance, this one here, squared. The square of the distance between them. If this one here is the product of the masses M1 and M2, we divide by the square of the mass of that distance apart. Then this ratio, the ratio of the mass to the square of the distance, is what we call the gravitational force. And to remove this constant, this proportionality sign, then we bring, if we remove this proportionality sign and we bring the proportionality constant, then we have that our Fg, the gravitational force is given by, G, which is the gravitational constant, times M1, gravitational constant times M1, M2, we divide this ratio by R. We divide this ratio by R squared. Yes? We divide this ratio by R squared. And this is the gravitational force that exists between these two bodies. And remember, these two bodies exerts gravitational pull towards each other. Understand? They exert towards each other. But now the magnitude of the pull is determined by the size of the body. If that of a greater mass is absorbed, it exerts force, attractive force on the smaller mass, and the smaller mass as well exerts attractive force on the greater mass, then the magnitude of the force exerted by the greater mass overcomes the magnitude of the force exerted by the smaller mass, and hence the attraction force of the smaller mass becomes minor and it is attracted to the bigger mass. And that is what exists between two bodies in the universe. And now if it is like that, and if it is agreed to be like that, then that is also explained. That is explained in our next line. And this is what we have just been discovering. Yes, we have been discussing these masses as it is attracted in the universe. Yes. Yeah. So this is what Newton derived in the early 17th century. Yeah. So if it is like that, then the gravitational force exists between two bodies in the universe. That is the space, right? The study is in the space. So as bodies exist in the space, they attract each other. Yes, the attraction is by the pull of gravitational force. So there you understand that the gravitational force is responsible for the existence of the attraction and repulsion between two forces, between two bodies and of masses, of course. So the gravitational force holds for the reason why bodies are attracted together and they hold in the universe together, in the space or in the vacuum together. So the force of attraction between two bodies gives us the origin of the existence of two bodies and attraction of bodies together, as bodies are attracted to each other. And then the smaller bodies are attracted to bigger bodies, depending on the magnitude of the force exerted, of the attraction force exerted to the bigger bodies. So that is where we explain our gravitational pull of attraction. Now, when we know gravitational pull of attraction, what is gravity then? What is really gravity? If so, we should know that. We should also realize that gravity is simply the pull of the object towards the earth. Now, yes, it is towards the earth. If it is so, the pull of the gravity towards earth is the pull of the gravity due to the gravitational force of the earth as one of the planets in the world, in the universe. You understand? So the universe do have a lot of planets, but now we are strictly restricting ourselves to the earth. The pull of the gravity, the pull of the planet is called, okay, the gravitational force exerts a gravity pull. That gravity is the pull of the object, the pull of the small bodies or greater bodies, if you may like. Yes, the greater bodies and the pull of the mass of the earth. Yes, the pull of the mass of the object to that body is called the gravity. To the planets, yes, we said bodies in the universe exerts attraction. Yes, but to the planets, as they attract objects, they attract through gravities. Yes, the gravity is now the pull of the object, pull of any object to it. The pull of the object to it by the gravitational pull of attraction is what we are calling the gravity to any planet, not only the earth. Yes, not on the earth, but now in our study now, we are studying the earth itself. So the earth exerts attraction, yes, the attraction of objects through gravity. You understand? So the gravitational pull of attraction exerts attractive force of gravity. So if it is so, due to the pull of gravitational force, and now we know that the pull of gravitational force is gravity, there is acceleration due to gravity. What is acceleration due to gravity then? Yes, in a single second, we know that acceleration due to gravity, then is just the acceleration gained by the object as it is pulled towards the earth by the gravitational force of attraction. We've just learned that there exists a pull of attraction between bodies. Now, if there exists pull of attraction between bodies, yes, this pull of attraction between bodies exists between the earth and the other bodies as well in the space. Now, the pull of attraction of the earth to the bodies, yes, the bodies are attracted to the earth by a gravitational pull. Now, this gravitational pull causes a gain in acceleration, This gain in acceleration is what we are describing to be the acceleration due to gravity. Yes, acceleration due to gravity. We here explain and describe it thoroughly as being the pull of the object. Yes, the pull of the object due to the gravitational force of attraction. We have learned that gravitation, as a reminder, we have learned that gravitational force of attraction is the force that exists between bodies in the space and the planet itself. And our planet today is Earth. The planet Earth attracts bodies due to the gravitational attraction. And this was discovered by, this attraction between bodies in the space was discovered by Newton in the early 17th centuries, as he derived his laws of attraction due to gravitation. Yes, let us imagine a ripened mango. What do you see? This is a tree with mangoes, a fruit, let me call it. This is a bunch of ripened fruits. Assuming they are ripened, they weaken in their attachment to the trees. Yes, the upper part of the attachment. When it weakens, it tends to be freely released from rest. As it falls down, the fruit tend to be released from a space. And then as it falls down, it gains a change in velocity from 0 to some velocity. And as it comes down, you can see that it is released and then it falls towards the earth. That means as it is falling towards the earth, there is a pull of attraction. Yes, that pull of attraction is the gravitational pull of attraction. It is pulled towards the earth. We have seen that they are attracted to the earth. Yes, those are small bodies attracted to the earth, being attracted to the earth by the force of attraction between their masses, the mass of the earth and then the mass of the small fruits they are falling. Yes, there's the mass of the earth and the mass of these small fruits falling down. Yes, these small fruits, when they're released in the space, because they have masses, they will be attracted to the ground. Yes, they're attracted to the earth itself, because here they will be released in the space. Yes, if they're released in the space, in the atmospheric boundary of the earth, yes, you are attracted by the earth gravity. Yes, we have just been talking about these points of gravity and what else. So you find that this gravitational pull of attraction will be attracting these smaller masses, because if the masses are greater than that of the earth, then they will be attracting the earth by themselves. But now, if the masses are smaller than that of the earth, and remember, mass of the earth is quite vast, that it doubles thousands and thousands and millions of these smaller masses. So we said the attraction of masses between bodies. If I could remind you in our whiteboard, we say that the smaller masses here do flow. They are overtaken. Their attraction are overtaken to the bigger masses. And we said, if this is our earth, this is now the earth. This is now the earth. Yes. This is our earth, and this is now the mango trees. I mean, the mangoes that fall in the space, in the vicinity here, and that distance apart here So they are attracted towards the earth. Yeah, you understand? So this attraction will be towards the earth. Yes, so that is by force of attraction here, the force of the gravitational pull of attraction. You understand? So that is what is being explained here. That is what is being explained here, that it is what is being explained here, that these mangoes, they begin to fall once they are released. They begin to fall freely from their space. And this is also explained from when you release a stone. Yes, when you release a stone, as it falls freely from down, from up down towards the earth. Yes, so we release them to fall freely from down, from up towards the earth. You understand? You find that these small masses are attracted to the earth, and as they are attracted to the earth, yes, that means they are being attracted by the gravitational pull of attraction between the body, the small mass, and then the bigger mass of the earth itself. So it is in the attraction. They also exert some attractive force to themselves, from the earth to themselves. But since we saw in the previous presentation that their attraction is overtaken by the attraction of the earth, because the attraction of the earth is quite vast and it is more greater than their attraction of the earth, then you find that the attraction of the bodies to the earth is more vigorous than their attraction of the earth. So they are overconsumed by the earth. So they fall freely to the earth as they are being attracted to the earth. So that is also the reason as to why we are advised to wait for the mango down from as they ripen and they fall. I remember I was told not to be climbing trees and over because I may actually also fall freely from the space as the branches may be breaking with us. So we may be practicing physics while we fall freely from the branches. Yes, yeah, you jump in the air, you try to go pick that ripened mango, but now you break from there. No support, you will be in the space and you fall also freely. Falling freely, remember, you are also practicing physics of gravity. Yes, you're practicing physics of acceleration due to gravity, but it is painful and it causes damage. You break your legs here and there. You may also end up dying. Watch out. So it is advisable we wait for the mango as they fall down, because we presume to prevent the effect of falling freely. Yes, if you go upstairs up the mangoes, you also fall freely and you end up injuring yourself because of the attraction of the forces. Between you, the falling body, and then the earth, which will be attracting you and hit yourself down due to the acceleration caused by the gravitational pull on you as the small mass. Our masses are just minor and we keep on being attracted on the earth. So we have to hold on and we wait our mango to fall freely due to the attraction of the earth on them as they ripen and they weaken, and they will as well be ready for us to eat right away from the ground. Do you ask yourself why they don't go beyond the earth? Yes, because they don't go beyond the earth crust, the earth surface. The acceleration due to gravity does not only stop on the earth surface. They are attracted and they stuck on the earth surface, because this earth, the soil we step on, they are hard and we cannot penetrate through. So we tend to stick on the surface of the earth, while there is a center of the earth that keeps on attracting us. The acceleration due to gravity acts at the center of the earth, and then we are attracted. Yes, we are attracted. If you step on the earth, just like you stand on the earth, just like this foot of the mango tree here, the foot of the mango tree here is attracted by its root to the earth surface. To the earth, to the center of the earth. So the acceleration of the body tends to act in the center of the body. So if we are like a ball like this, so we are attracted in the center from the surface. So we don't penetrate through, and we stick on the what? On the earth surface. And that's why all the bodies are attracted on the surfaces, and we are also included. We are also included on it, and that's why you find your mango just there, stable on the earth surface. They cannot penetrate to the core of the earth because it is hard for them to fall inside. But when they get a space, yes, they continue down, just like when they fall in a pit. Yes, they continue down. They continue until they reach the bottom of the pit. And the pit latrine, of course, the pit dug, of course, of such a different fit. So they tend to penetrate through any vacuum space until they reach the center of the earth. So it is the reason as to why we find our mango fruits just there on the surface, and once they fall in a pit, they continue down, yes, until they find a resting point. That's the reason as to why they continue. They are tending to be attracted towards the center of the body, and that body is today the earth itself. Thank you, Garrett. Try to understand that the acceleration due to gravity is what is responsible for our standing on the earth's surface. As our next presentation may show, we now know that acceleration due to gravity is a rate of change of velocity. Acceleration due to gravity has a rate of change of velocity. That is change in velocity per unit time taken for that velocity. Yes, then the unit, the standard international unit for the acceleration as a general, because it is just a rate of change of velocity. Yes, so the standard unit is meters per second square, because it is like meters per second of that velocity. Yes, it is meters per second. As we can go to our chalkboard, our whiteboard here. Yeah, we said, let me open a new board. Good. So we said velocity is measured. What is the measurement for velocity? Velocity is measured in meters. In meters per what? In meters per second. Sorry. Yeah. So is measured in meters per second. That is velocity. But we said acceleration is what? We said acceleration is given as velocity. It is like change in velocity. Yes, acceleration is change in velocity. That is delta V divided by time, and this one is divided by time. Delta V divided by time. What is delta V? Meters per second minus meters per second. The physical measurement is meters per second. The final SI unit here will be meters. The final SI unit will be meters per second. If it is meters per second, we divide these meters per second by another second. I'm taking the SI units. If it is meters per second divided by divide by another second, then this one here finally becomes what? On a final note, we shall have meters. We shall have meters per second squared. Yes, meters per second squared. That means you're dividing by time twice. So this one becomes our final. This one becomes our final unit, the final physical derived unit for acceleration due to gravity. Okay, acceleration as a general. Yes, it is acceleration as a general that is measured in meters per second square. So we also adopt that measurement for acceleration due to gravity. You understand? But now, if it is changes to acceleration due to gravity, then we denote it to be g. Yes, we denote it to be g, and this g is given to be, it is practically determined to be 9, it is 9.81. Experiments has ever found it to be 9.81 meters per second squared. Yes, meters per second squared. That is what experiment has ever shown. And I, for one, I have also managed at least to get something closer to this. I managed to make 9.83, 9.84. Yes, I managed to make it in my lower class. And I also tend to conduct this determination as we may be uploading the video later on. Yes, we shall be uploading the video later on after this determination of acceleration due to gravity as an experiment itself. So I wish you hit the subscription button such that you get this determination later on. Yes, we shall determine acceleration due to gravity as it comes to 9.81 meters per second. So our struggle is to get 9. That is on the Earth. The acceleration due to gravity on the Earth is determined to be 9.81. And it changes from planets to planets because they have different gravitational pull of attraction. The magnitude of the gravitational pull of attraction of the planet determines the size of the acceleration due to gravity in such a planet. That is what experiment has shown in the planet Earth. Yeah, so acceleration due to gravity is measured in meters per second square, and on the planet Earth, we found to be 9.81 meters per second square. That's great. But now, having known acceleration, gravity, and acceleration due to gravity as a whole, what are the practical examples in real life? Acceleration in real life. What can you say? Acceleration in real life. What are the real life explanations, real life examples that shows acceleration due to gravity? Yes? Puzzled? Are you puzzled? Can you think of something? We've just been talking about mangoes falling, what? Supposing you release a block, just a piece of wood, a piece of matter that has weight from a particular height above the soil, above the earth's surface, within the reach of the atmosphere. Yes, the atmospheric boundary of the earth. Where do you think it will be going? As a practical matter, yes, if I take this piece of dry leaves, yes, these 2 pieces of dry leaves, if I release them from this height, where do you expect them to be going? This is one of the real life examples of acceleration due to gravity. Yeah, I tend to see where they will be going. One, it has gone down, right? It has gone down. Another one is going down. Acceleration due to gravity in real life example, release any piece of matter from above your surface, from above the earth's surface. Imagine pouring water down, pouring water. If there was nothing like acceleration due to gravity, it would not go down. It would go elsewhere. But then because water has weight, it is attracted to the earth, it will be flowing downward to it. Unless pushed, it can never be upward. And you can even witness me, you flow water, you pump water upward, it will still tend to come down. Reaching a certain height, it comes down. Those are some few examples. Imagine a free-falling body. Here our first example comes. When you release a paper, that's a piece of paper, you think it might not be having weight, but where will it go? It has weight, that proves. Practically. We have just seen this piece of dry what? this piece of dry leaves. When you release it, it goes down. Yes, you release it from a particular height. Yeah, it goes down. The same way, if you do it with a tissue paper, and you release the tissue paper together with this dry wood of, dry leaves of mine, or you change that situation. You bring a steel. Yes, you bring a steel, just like my bunch of key here. The bunch of key and the hood. Which one goes faster? You find that? Yes. You find that the key will tend to move faster than the key will tend to move faster than the bunch of key will tend to move faster than the leaves. So the key is a steel and the leaves is just a leaf. They have different weight. They have different weight and they are attracted differently to the earth's surface. You understand? So being attracted differently, that's the same as our example is being given up here, given up between tissue paper and a steel bottle. Which one will fall faster? The steel bottle will fall faster. Another real life example comes in the satellites orbiting around the planets and celestial bodies like moons on the Earth and other planets. Remember, just know moons are attracted, and other celestial bodies are attracted to the planets they orbit, they rotate upon. Orbiting is just rotation about the planet itself. So these various planets are orbited. The satellites and the celestial bodies moves around the planets. Yes, and they are attracted to be in their position around the planet by the pull of gravity. The pull of gravity. And why? Why do you think they are not absorbed to our, why do you think they are not absorbed inside? And why don't we see those bodies on the what? On the earth surface? A question, think of it and give me an answer down in the comments. I'll see and find a way of explaining itself. But then, just they have also a repulsive force. But since the earth surface, the earth has more of its attraction, then just they will be attracted, but they also have some opposition. Yes, they will be opposing also the attraction of the earth, the attraction of the earth, and these satellites remain in their position, attracted and repelled, then they also remain at the same point. So gravitational pull of attraction does a lot on the satellites and the moons. Understand? So the next one is what we have been discussing: the falling of fruits, the free falling of fruits. The fruits fall from the trees after it ripens because the mass of the object increases and the attachment weakens. As the attachment weakens, yes, as the attachment weakens, you find that the weakening of the attachments, the weakening of the attachment releases the fruits to fall freely, and you find that the fruits fall on the ground surface. They do not fall up, they fall down. Yes, you don't fall up because they're still in the vicinity of the earth. Falling down shows that there's attraction to the earth, and that is acceleration due to gravity. Thanks, friends. That's the precision I want you to draw in all this discussion. You understand? So we have to know that there exists acceleration due to gravity. There exists acceleration due to gravity as it goes down. I'm sorry, my network is quite disturbing. Appreciate that. Yeah, I appreciate that. So it is attracted on the earth because of its force of attraction. And then you find that, being attracted, yes, you appreciate that being attracted will hold us responsible to explain, responsible to explain the fact that they fall towards the earth's surface. And here we have to note also that, it is really not the gravitation, or gravity that is different from each other. The term gravitation and gravity is not necessarily different from each other. They are used interchangeably. If they are used interchangeably, then you can say gravitational pull of attraction or the pull of gravity. You're still meaning the same thing between two objects with masses or energy. Yeah. So you appreciate the fact that it is a mass or energy that pulls the bodies together. So it is gravity, either gravity or gravitation. They tend to mean the same thing, because gravity is the pull of attraction to the earth, and gravitation is the force that attracts, the gravitational force that attracts bodies together. So gravitation, gravity, they tend to be used interchangeably. And it is also notably correct to realize that gravitation cannot be held responsible for the people falling in love. Yeah, one of our scientists, Albert Einstein, noted that it is not gravity, it is not gravitation, neither is it the gravitational pull of attraction that holds people responsible for falling in love. No, it is not such a fall in love. When you say I fall in love with you, it does not mean the gravitation that pulls me to you. No, other factors matters. That is what is explained also in this German, in the German version of Einstein's statement, the original statement he made when he was interviewed in the year 1981 in a footnote of his letter, as he replied that to the journalist. So we have to take such in note. I appreciate your time you spent with me. I appreciate it, and I just know you didn't waste it. You have to bear with me the challenges we faced as network and other factors. So I appreciate that. And this evening, I end my discussion here. If you have a question to me, you leave it in the comments. If you have other comments, I wish to see it in the comments as well, the comment button below. Never forget to hit the subscription button and support me through comments and other support that you may render. Thanks for that. I appreciate the fact that you have all come to the end of our meeting today. Thanks for that. I appreciate that, and I wish to end our discussion here. Thank you. See you in the next video. Thank you. Bye-bye.